Welcome to all in the lecture series of functional analysis. Now in this lecture we see the theorem. If a norm space capital X has the property that the closed unit ball capital M with a set of all small x belongs to capital X such that norm of x less than or equals to 1 is compact, then capital X is finite dimensional. Now to prove this theorem we use the method of contradiction. That means here to prove that capital X is finite dimensional, here we assume that dimension of X is infinite and then we show that this leads to a contradiction. So we start the proof. We assume closed unit ball capital M set of all small x belongs to capital X such that norm of x less than or equals to 1 is compact, but dimension of x that is equals to infinity. That is our assumption. Now here dimension of x it is equals to infinity. That means x must be not equals to 5. As it is not empty, so we may choose a point. We may choose a point say x belongs to capital X. Now x belongs to capital X. With this x we define another point x1 that is equals to x divided by norm of x. Now small x is the element of capital X. 1 divided by norm of x is a scalar. It is a scalar. And capital X is a vector space. As capital X is a vector space, therefore it is closed with respect to the scalar multiplication, and therefore x into 1 by norm of x that is equals to x by norm of x, that is again the element of capital X, because small x is the element of capital X. It is a scalar. Capital X is a vector space, therefore it is closed with respect to the scalar multiplication, and therefore x divided by norm of x is the element of capital X, and that element is nothing but x1. x1 belongs to capital X. In this way, from any point of capital X we can make a point x1 such that norm of x1, now norm of x1 it is equals to norm of x divided by norm of x, and now it is equals to norm of x divided by norm of x, and that is equals to 1. That means from any point of capital X we can construct a point whose norm it is equals to 1, and therefore we can write here we choose a point small x1 belongs to capital X such that norm of x1 it is equals to 1. Now this singleton x1, this x1 generates a subspace. Say capital X1, whose dimension is 1. Now with the help of this vector x1, this generates a subspace. We give it the name x1. Then this the dimension of this x1 it is equals to 1. Now dimension of x1 it is equals to 1, which is strictly less than infinity, and infinity is the dimension of capital X. And here we know that x1 is the element of capital X, and this x1 generates the subspace x1, and therefore this x1 is a subspace. It is a subspace of capital X. Again here we write down this statement like this, that is x1 is a finite dimensional subspace of a norm space capital X. And as it is a finite dimensional subspace of a norm space capital X, therefore by theorem, that theorem is 2.4.3 in the book about the functional analysis, introductory functional analysis by Erwin Kreyszig. In that book, the theorem 2.4.3 says that every finite dimensional subspace of a norm space is closed in that norm space, and therefore here, as x1 is finite dimensional subspace of a norm space X, we can say that x1 is closed. Now, by using that theorem, as x1 is finite dimensional, therefore it is closed. Now, x1 is closed. Again here, the dimension of x1, it is equals to 1, which is strictly less than infinity, that is the dimension of x. Now, this condition implies that x1 is a proper subspace. x1 is a proper subspace of capital X. x1 is a proper subspace of capital X. From this, here we get that x1 is closed, and here we get that x1 is a proper subspace of X. Now we apply these two conditions, and we also apply the Rees lemma. The statement of the Rees lemma is like this. Rees lemma. Let capital Y and capital Z be subspaces of a norm space capital X. Of a norm space capital X, and capital Y is a proper capital Y is closed and is a proper subset, and it is a proper subset of Z. Then the Rees lemma says that then for every real number theta, in the open interval 0, 1, there is a small z belongs to capital Z such that norm of Z equals to 1, comma, norm of Z minus Y, that is greater than or equals to theta, for all small y belongs to capital Y. This is the statement of the Rees lemma. Now here we have to use this Rees lemma. Here we have to given that capital Y and capital Z be subspaces of a norm space capital X, where capital X be is of any dimension, and also here we have to given that capital Y is closed and is a proper subset of Z. That is we have to given. Then Rees lemma says that for every real number theta in the open interval, there is a small z belongs to capital Z such that norm of Z equals to 1 and norm of Z minus Y, that is greater than or equals to theta, for all y belongs to capital Y. Now here we have to use this Rees lemma to prove the theorem, and therefore here we have x1 is closed and x1 is a proper subset of capital X. As x1 is closed and it is a proper subset of X, here we can say that x1 and x with the subspaces of a norm space X. Here we say that x1 is a closed and it is a proper subset of capital X. Then by using this Rees lemma, then by Rees lemma. Then by Rees lemma, here we can take the value of theta equals to half. For 1 by 2 belongs to the open interval 0, 1. There is a small z belongs to capital Z. Here we say that for half belongs to the open interval, we say that there is small x2 belongs to capital X such that norm of x2 equals to 1, comma, norm of x2 minus x1 that is greater than or equals to 1 by 2. Now here we apply Rees lemma to x1 and capital X. Now here we get the two elements, that is x1 and x2, both are the elements of capital X such that norm of x2 minus x1 that is greater than or equals to half. Now these elements, that means x1 and x2, these two elements generate subspace x2 of capital X. That means every element of capital X2 is a unique linear combination of these two elements x1 and x2. Then dimension of x2 that is equals to 2, which is strictly less than infinity, that is equals to the dimension of x. Again here we get that x2 is finite dimensional subspace of a norm space X. As x2 is finite dimensional subspace of a norm space X, therefore again by using the theorem, by theorem 2.4.3, here we get that x2 is closed in capital X. As x2 is closed in capital X, and we know that x2 is a proper subset of X. Again by using the Rees lemma, therefore by Rees lemma we just repeat this process. By Rees lemma, for half belongs to the open interval 0, 1, there is x3 belongs to capital X, again such that norm of x3 that is equals to 1 and norm of x3 minus x that is greater than or equals to half for all x belongs to x2. Now for each x belongs to x2, we have norm of x3 minus x that is greater than or equals to half, and we know that x1 and x2 these are the basis element of x2, and therefore x1 and x2 they are also the element of x2, and therefore here we say that norm of x3 that is equals to 1, norm of x3 minus x1 that is greater than or equals to half, as well as norm of x3 minus x2 that is also greater than or equals to half. Now in this way, here we get the element x1, x2, x3 in such a way that the norms of all these elements it is equals to 1. Also we get that norm of x1 minus x3 that is greater than or equals to half, norm of x3 minus x2 that is also greater than or equals to half. Also we get that norm of x2 minus x1 that is also greater than or equals to half. Now proceeding in this way, we get a sequence xm. Now each xm is an element of capital X. We get a sequence xm in capital X such that norm of xm it is equals to 1 and norm of xi minus xj it is always greater than or equals to half for all I not equals to j. In this way we get this situation. Now in this sequence the norm of each element it is equals to 1 and as it is its norm it is equals to 1, that means for all m each xm it is the element of capital M by using the definition of capital M. Therefore, for all m xm belongs to capital M, it implies that sequence xm is a sequence, it is a sequence in capital M. Now it is a sequence in capital M such that norm of xi minus xj it is greater than or equals to half. As norm of xi minus xj it is greater than or equals to half, it means that this sequence does not have a convergent subsequence because their difference is greater than or equals to half and therefore this sequence does not have a convergent subsequence. Is a sequence in M such that this sequence xm does not have a convergent subsequence. But this gives the contradiction to the definition of the compact set does not have a convergent subsequence. This gives the contradiction to the definition of compactness because here we have to given that capital M is compact. As capital M is compact, that means it is sequentially compact, and the definition of the sequential compactness is that every sequence must have a convergent subsequence. But here we get the sequence xm in capital M such that this sequence does not have the convergent subsequence because the difference between any two distinct element of this sequence is always greater than or equals to half and therefore this sequence does not have a convergent subsequence and this gives the contradiction to the definition of compactness. This gives contradiction to the definition of compactness. And therefore our assumption is wrong. Our assumption is that dimension of x it is equals to infinity is wrong and hence dimension of capital X it is strictly less than infinity and this implies that capital X is finite dimensional. And hence the proof that the norm space capital X is finite dimensional.